Okay, we just give you the concept on the determination of French speed of a premixed frame based on the balance between the supply velocity and the French speed. And then your friend will set a certain position, then you can identify the French speed is equal to the supply velocity from the premixtures in the upstream side. But in many cases, the balance between the supply velocity and the French speed is imbalanced. Then what do we do? What kinds of behavior you will find? Actually, there are two different kinds of French characteristics you need to learn it because they are very important for the application of a premixed frame. One is the so-called the blow-off. The blow-off means when you go back to our dog, as you remember, this dog can eat the meatball as the ability of the 5 meatball a minute, right? And he can eat five meatball at 1 minute. But in this case, initially this dog is sit very nicely at a certain positions and just waiting for the supply of meatball. But if these guys they supply the meatball continuous has a larger number. For example, is 6 or 7 meatball a minute. That means this dog will feel that because for a minute he already eat 5 meatballs, but additional 1 or 2 coming in. But this dog cannot fit in, cannot eat this additional 2 meatballs. There is only one way this dog will move back, try to avoid this 1 or 2 meatball additional, right? That means that this dog will try to shift the position to a longer distance away from the upstream side supply, the upstream supply side, and to reduce the supply velocity, supply intensity to its side. And this movement, actually, they tell you this is so-called the blow-up regions, blow-up behavior for premixed frame. Okay, and these kinds of frame structures you can see usually in your gas stove in your kitchen. For example, here you can see this is a regular, very nice cone frame, right? But for example, here you try to fix your concentration of premature. For example, this for this case, because you have a very broad blue frame, right? Which means the frame may be closer to the stoichiometric ratio a little bit richer. Okay, so you can have some diffusion frame in the surrounding. But now you will find out, for example, this is maybe it's 11% of methane mixed with the air. Then friends ship very nicely. But now you try to keep the mixing ratio at the same, but increase the injection velocity. What's the meaning of increase the injection velocity? That means the actual velocity approaching to premixed frame is increased, right? When you increase the U, but the concentration is fixed, that means that your SL is fixed, but your capital U is increased, then your sine alpha, the angle will be reduced, right? Will be reduced. Reduced means your cone will become, has a longer length, become more, has a smaller angle, and this will move to the downstream side. Okay, the length of your cone frame become longer and longer. Okay, this is the first step. This frame will move to the downstream. I hope you remember if the balance between the supply velocity and the frame speed, and you can have a frame sit here. Now you try to change your concentration from the rich side to the lean side. You will see the frame shape will reduce and increase by this way, right? Okay, the moment. And for this kinds of movement, basically with the discrete based on the fixed injection velocity. But now, if you fix the concentration, that means that you fix the premixed frame burning intensity. Now you try to increase your flow velocity, you will find out initially the frame shape is smaller, then they will increase continuous with a higher frame length if you increase the injection velocity, okay? Because this frame need to move to the downstream side, to balance with the increasing injection velocity. But when you do the continuously increasing the injection velocity, you will find out here is something happen. This friend initially they sit very nicely at the base of the exit of your burner, but finally they cannot sit here because they lost the stabilization at this point, and they just have a possibility, and they have a 1 point attached to the burner edge, and maybe in this case they start to fluctuate. Actually, in many cases, if you continuously increase your flow velocity, this flame will be pushed away. That means that you do not have a chance to stabilize a premixed flame in this flow, because flow velocity is higher than your flame speed. For example, if you have a, in our previous case, let's go back to a little bit here. Okay, here assume the concentration ratio as we identified from the previous experiment, and you can see for given premixture you will have a given propagation speed. For example, here there is the 40 from your concentration, we can determine your flame speed around 40 centimeter per second, right? Okay, and you try to increase U continuously. Okay, if you for your sine alpha should be less than 90, so 45. Okay, then this one you continuously increase. Sometimes this one will increase to a much higher than your SL, 40 centimeter per second. That means that your friend has no possibility to sit in the given flow field of your Bunsen jet. Okay. Now, in this case, why this flame can stabilize at a certain point, because they still have a diffusion flame support here. But in this condition, actually the flame dip away from the port of your burner, means the burning velocity cannot, the flame speed cannot balance with the injection velocity, and the injection velocity is much higher than the burning speed. Then they need to move to the downstream side. If the injection velocity is too much, then premixed flame cannot sit at that positions. Then easily they will disappear completely from the flow field. This is a so-called the blow off. Typically, in our the burning combustion chamber in the industry furnace, usually they have a very high speed. They flow high speed. You do not have a chance to stabilize your premixed flame at certain position. Then you need to do some special design. I will tell you soon. Now the other one, if your flame speed is higher than the supply velocity, okay, they tell you this dog originally has ability to eat the meatball 5 meatball per minute, but this guy just supply 3 meatball in a minute. That means when this dog already eat 3 meatball, but this dog waiting for the continuous 2 meatball coming in, but he cannot get these 2, right? So this dog will try to find additional 2 meatball to fit his capabilities. Then this dog will move to the supply of meatball site. That means this dog will move to the this guys in these directions. Then we call this a so-called flashback. Okay. What kinds of behavior you can experience? Actually, we go back to your gas stove burner. I hope you remember when you turn off your gas stove, what happened, you can experience. Usually where you will see some bone, right? Why is this? The bone represents the flashback of your gas stove frame. Let me tell you, when you look at your gas stove, usually the design always give you a very small, tiny flame, right? And those holes are very small. Why? This is a very important design. We call this the diameter of your pore is the so-called quenching distance. Quenching distance means this small hole is the design for this small hole is good enough to prevent your premixed flame propagates into your burner. Let's look at a simple problem. For example, there is the port, you supply the natural gas coming out, okay, and then you produce the small flame. And when you try to reduce or close or turn off the natural gas supply, when you turn off, there is a, from the your valve or your valve to the exit plan of your gas stove has still have a piping, right? Now you continue supply the fuel, okay, continue to the gas stove. When you close it, when you turn off the valve, then suddenly the flow will stop. But inside of the tubing between the gas stove surface and the valve, they still have some premixture exist, right? But they suddenly lost their momentum. Actually, that means that the velocities disappear. They do not have actual momentum. The flow do not have a pressure to push them out. But in outside of the gas stove, there's still a flame, right? Flame has its own flame speeds. Now you can imagine in the beginning, the supply of the premixture is satisfied by the burning flame. Then this flame sits very nicely at the surface of your gas stove. But suddenly, the supply velocity disappear. Disappear means your premixture in this part, in this tubing, still exists, but they become stationary, which means the flame has its own propagation velocity. Then this flame will start to propagate to the source of your supply. That means this flame will move into your tube. Okay. Now you understand this is a reason why you need to design a small diameter of your port. You can imagine now when you close when you turn off your gas stove, now the flame should be this flame should be propagated into the tube, right? When you have a premixed flame propagate into the tube, because inside of the tubing, there always the premixture. Premixture means that you mix the fuel and the oxygen very nicely. Then that means at any point they have a possibility to burn. Then when they flash back into your systems, into your tubing, then they will make the explosion. Okay, you need to prevent the flames, the small flame will be extinction before they propagating into the tubing, which means when you need to design a small port. And this small port is good enough because the small port, that means in the surrounding there is a solid material, right? When the flame approaching to the port, they will have a big heat loss to the solid surface. And this heat loss is good enough to extinction all the premixed flame propagating into in the tubing. If the diameter port is too large, then you may just extension the periphery of your premixed flame. They still have a central portion of your premixed flame will penetrate into your tubing. Then this will make a disaster for your gas stove. Okay, and you will find out when you have a flame propagate approaching to the port. I mentioned this propagation basically is a diffraction wave. It's a wave that will produce the pressure fluctuation. When this flame approaching to the hole, to the port and the extension, but they already produce some kinds of pressure fluctuation, then you will see the boom, the sonic wave occurs. So every time when you turn off the gas stove flame, you always can feel this kinds of the flame propagate back, flash back, and produce those kinds of pressure wave and a sound effect. And this is a typical behavior you can experience in your kitchen. Then we call this as a flashback. And when you go back to, we already explained the supply velocity imbalance with the burning velocity, then you may have a flame blow off or flashback. The design for the flashback, usually you need to think about the so-called quenching distance for the application of gas stove in your kitchen. The ports should be small enough, okay, to prevent the flame propagate into the tubing of your gas stove system to prevent the explosion inside of the tubing. But for the flow blow off, because usually for application of industrial furnace, the flow velocity are pretty much high, you cannot find a suitable location to have a smaller flow velocity to fit with the flame speed. Now, some typical application can be used in real case. For example, blood body effect that we learned from the fluid mechanics, right? If you have a blood body here, then you have high speed flow from the left hand side. Usually, those flow will be decelerate in front of your this blood bodies and reduce the velocity to zero at the surface, right? Which means if you have very large value, but you insert the blood body into your high velocity flow field, you always have a region to have a lower velocity up to zero. Okay, at these positions, you may have a possibility to find out a lower flow velocity point to fit with the burning velocity. Okay, you can see usually when you have a blood body insert into the reacting flow with a high speed, now you will produce the so-called recirculation zone or wake region in the downstream side of your blood body. You learn from the fluid mechanics, and when you ignite it, you will find out the flame can be established attached to the near the surface of blood body and extend to the farther downstream. Okay, this is a typical application. Try to use the blood body insert into high-speed flow field to decelerate local flow velocity. Then this decelerate local flow velocity has a possibility to meet with the lower magnitude of flame speed. And this is a good location for stabilize your friends in your premise flame in a high flow region. Then we call this kind of design as a so-called flame holder. Okay, we use the flame holder in a very high flow speed flow for premixed burning. And there is several design for application. The first one, as I described, the blood body, you may use a sphere or cylindrical shape, or you can use a so-called V-gutter. V-gutter means the V shape and with a circle, and they can stabilize, they can produce the local low-speed region. Then you can have a flame propagation stabilized in this region to burn out all the premixtures. There is another one is easier to be observed in industrial application for the burner. There is the sudden expansion flame holder. When you flow in the center part has a high velocity, but you try to produce a sudden expansion, then you will produce the so-called recirculation zone here. When you have a recirculation zone here, that means that you will have a separation stagnation plane, and along this stagnation plane, the flow velocity will be reduced. You can have a possibility to let your premise flame stabilize here, continuous burning. Okay, and the right hand side tell you, okay, this is a sudden expansion design. You can see there is a sudden expansion, right? This is an H. The center part has a small diameter, but suddenly here there is the expansion. Then this region near the wall will have a recirculation zone. This recirculation zone will have a region to have as a reduced flow velocity to stabilize your flame. The other one is opposed jet flame holding. You give another jet impulse and inject against with the high-speed streams. Then you will have a stagnation plane here. And in this region, as you remember, the flow velocity, actual velocity will be reduced. Then you will have possibility to initiate the flame continuously. Then this is the typical design for preventing the blow-up catalyst for given premise flame. And I mentioned how to prevent the premise burning through the flashback. You need to use the small pot, a small pot for your burner. In general, for the industrial application, people do not use the premise flame in general. Why? Because for industrial furnace, they need to provide a big amount of premixture into your combustion chamber, which means you need to have a large pot or supply mixtures. when you have a large pot, now you need to have a better design to prevent flame flashback. Okay, it is very hard to design a good design to prevent the flame flashback for a large size burner. Then people will not use the premixed flame in industrial application. Usually, we use the premixed flame in our gas stove. Okay, and there is some consideration from the pollutants, or we call the emissions, and you need to have a different kinds of design for application. And I give you this experiment we have 20 years ago. At that time, we tried to study the flame stabilization in aircraft. Okay, and this is a so-called the afterburner. Actually, this is not a good result because but this is a good pictures to tell you the configuration of our experiments. Here, this is a so-called afterburner. Afterburner means for aircraft. They always has a so-called afterburner in the downstream side of your gas turbine, because after the combustion for the gas turbines, they still have some air, and those air is supplied from the earlier compressor already consume some energy on it, and we need to use it. Then when aircraft air fighters, especially for air fighter, when they attack the other air fighter, then they try to escape very fast, very efficient, right? Then at that time, they will supply more fuel to the afterburner to increase the energy release, to increase the thrust, to push your air fighter has a high acceleration velocities. Then that means this is afterburner, and here you can have a V-gutter because in the region of afterburner flow velocity is very high. You need to have a so-called V-gutter here to stabilize the flame in the downstream side. This is the first design, but we do not control well on the flow velocity. That means that in this case, actually, the flame is already flushed back into the upstream side. There is a fuel bar here, and the flame exists here, and they already produce a high temperature gas, and those high temperature gas passing through the burner, the afterburner is was made by steel. Then you can see the steel has show you the reddish color because the temperature is quite high, because the hot gas coming from the upstream side hit on this afterburner. But later experiment will try to increase the flow velocity. Then they push the flame. Blue flame will stabilize in the downstream side of V-gutter. Then you can see this is exactly experiment observation. Okay, you can see there is ignition. This is ignition part here. Okay, then you can see the flame exists on the edge of the afterburner and also the V-gutter. And this is a typical experimental observation to see how to stabilize the premixed flame in a high speed flow field. Okay, and this is basically a flame holder, and those flame holder is used to prevent the blow off of your premixed flame. Okay. Okay, this is the we go back to the slides. Then you can see there is the conclusion for the classification of the flashback and also the blow off. You can see, for example, here for the D in the case. Actually, I try to explain this. The solid line actually represents the flame speed of your given premixtures. For given premixture concentration, is fixing ratio is fixed, right? Then the burning intensity flame speed is actually is a constant when you do the evaluation around the radial positions, they will reduce when they approaching to the rim or the edge of your burner because of heat loss. Okay, and heat loss, when you have a heat loss, burning intensity is reduced and the flame speed is reduced. And the dotted line represents the normal velocity you may have from the injection velocity, depend on what kinds of velocity distribution. For example, you may have a uniform actual velocity distribution, or you may have a parabatic velocity distribution. And we try to think about the normal velocity, flow velocity approaching to the frame. And you need to think about the balance between the frame speed and also the normal velocity. Okay. For the case of the so-called stable frame, you can stabilize the frame at this burner, because here you can see there is a region you can in the center region, the frame speed is smaller than the local velocity, normal velocity, right? And you will figure out this frame will be pushed back to attach with the normal velocity here. But for this region, since the flow velocity is smaller, okay, then this frame will move to the upstream side. By look at these figures, you can see in the center portions, frame will push back to the coincide with the dotted line. But these portions, the frame will move forward to coincide with the dotted line. Then they will establish a suitable cone frame or sit at this jet frame. Okay, we call this as a possibility to have a stable frame. But for C is a critical one, because in these regions, in the center region, the flow velocity, normal velocity is much higher than the frame velocity. In this region, it is almost impossible to stabilize frame at this at the position for the dotted line. Then they have a critical point. Okay, but if you look at the B, if you increase your actual velocity, the normal velocity even higher, they tell you there is no possibility to give you positions because the flow velocity is too high compared with the frame speed. That means that you do not have a possibility to let your frame sit in this region, and we call this as a blow off. Blow off means that your supply velocity is too high and push your premixed frame is out of your flow. Then you cannot have a frame stabilizer in this region. But for the case A, the frame speed is much larger than the flow speed. Definitely, they will move forward to penetrate into the interior tube of your supply end, and this we call this as a flashback. Okay, then when you look at these 4 figures to tell you how to give you an idea to think about the position of your premixed frame based on the balance between the normal velocity on the flow velocity on the frame surface and the frame speed. And here, yeah, that is the frame holder I already explained to you, and I give you some example to understand how to hold your frame in a high flow region.